Okay, welcome to the Chapter 4 labs. This is going to be divided into two parts, and what we're going to do first is we will look at discriminant analysis using R, and then we will, in the second part of the lab, move into logistic regression. So let's just start off here, and the first thing I'm going to do here is write, we'll call this code performs LDA, QDA, and RDA. And the RDA, we're gonna sort of do RDA. There's actually a problem with the package, and I noticed it this morning when I was looking to run the code here. And so let's see, it's the 3rd of October already. And anyways, about the RDA, I emailed the creator of the package, so I will have to see if we can update that once I hear his response. So the first thing we'll do is we will remove all of the memory, clear the memory here. And I'm going to load 3 packages. Okay, one is called MMST. This is from that multivariate book that I showed you by Eisman. And the next one I'm going to load is called KLAR big R. Okay, and if you want to get this package installed, you can do install packages, KLAR. And so the thing with this package, this is the one that contains the stuff for RDA, and I'll talk about that at the very end. I'll talk about this package at the very end. But it's somewhat outdated, so you might get a warning when you do the installation, which says that this was compiled on an earlier version of R, and that's okay. It will still load, but that's probably where the error is coming from when we do RDA. So I'll set the working directory, and I'm going to cheat. Okay, I'm going to go into my computer here, and I'm going to find where I have the code. And I'm just going to copy and paste this so I can get the path. Okay, and then I will just do set WD, put it in quotations, and now let's just run this and make sure we're in good shape. Okay, so here, this is the warning you will get. So this package was built underneath an earlier version of R, and I'm running the latest version here. And so what happens with R is that, as you know, there's a bunch of different libraries that you can install to get different functions, and but one problem is that the people who create the functions are just people like me in the libraries, and we don't always have time to update. R releases a new version quite frequently, and this version probably isn't all that old, but unfortunately the backwards compatibility is what we call it. Doesn't always carry over. So, in other words, KLAR was working well on the other R system, but now it seems like with the new version of R, there's something that has to be kind of sorted out here. And that's common. We see that from time to time. So, what we're going to do is we're going to analyze a data set about Pima Indians and pregnancy. And this data set is part of the Pima data, which is stored in the MMST package. So in order to load the data, we will actually use the command data and bring it in. It's called Pima. And this is a famous data set. It's also in the machine learning repository. If I do help Pima, I can see that it's in the MMST package, and it's about diabetes. So this particular group of ethnic individuals is kind of predisposed to gestational diabetes, which is the kind of diabetes you get when you are pregnant. And it's it can occur with pregnancy. It's not necessarily that these pregnant women are diabetic before they conceive, but it's something that can manifest during pregnancy. And so here there's 532 observations and there's 9 variables. And there are different kinds of variables. We have the number of pregnancies, glucose, blood pressure, a skin fold thickness, body mass index, a pedigree, which gives some idea of the degree of ethnicity. We have age and a class digit and class. And so this is kind of redundant, right? We can actually just work with class. So here, if I do head PIMA, I can get a feeling for what this looks like. Okay, so I'll just do head PIMA, and so I'm just going to use class here because I wanted to know it's a class level factor, and so I don't need to do this. So I'm going to actually create another data set from this PIMA. So you could call it my PIMA, and I like to do this now. So one thing we could have done. Well, let's do it first, and then I'll talk about what we could have done. But I'm going to use the whole PIMA data set, except I'm going to eliminate 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to eliminate the 8th column, so I do -8. Okay? And let's take a look. So now if I do head, my PIMA, okay, we're in a good spot. So that class digit piece is gone. So we have to kind of check the data for that. Another thing we could have done is we could have operated directly on the PIMA, and I could have said the new PIMA set is the old one, -8, but I don't like to use that because if you run it too many times and you start writing over the data set, you can start to lose other columns and whatnot. So it's just easier to call it a new variable. And so one other thing to look at, if I go back to head PIMA, which was the original data set, is the coding here. So here they had 1 as being diabetic and 0 being normal. Okay, so we want to kind of keep the coding in mind, and we're eventually, when we go to compute the misclassification rate, we're going to have to recode this, and we'll recode it. It doesn't really matter which one is 1 and which one is 0. Typically we say the event is 0, but it turns out the way they can compute the confusion matrix and the sensitivity, that with R and the package, it's a little bit more natural to have 0 be the diabetic, because 0 is the event when we use the confusion matrix, which we won't use that until the next lab, but you'll see what I'm talking about. Okay, so far so good. Another thing we might want to do is we might want to, if I look at head, my PIMA, we might want to look at the correlation of the data, make sure there's nothing really redundant. And here we don't want to use the last column because it's a factor, but we'll use the first 7. Okay, so let's just take a look at the correlation. There's nothing here that's really standing out at me. Age and the number of pregnancies is something. The other thing which I expected is that skin fold thickness and BMI are highly related. In fact, a lot of people know that if you're kind of into your health and you have your BMI tested, if you ever went to a gym, they usually also pinch your arm and take a more thorough measurement. They factor that into the BMI, so they are in fact related. So, okay, but so far I think I want to keep all my variables, so we'll just keep it like that. And what I'll do here is I'm going to create a test and training data set. And maybe I will set, I think is it set seed? I'm getting my MATLAB and my R mixed up, but I'm going to set the seed because I'm going to be sampling the data set, which is, the analog of picking numbers out of a hat for the different samples. And I want to be able to recreate this. And so for the training set, what I'm going to do is I'm going to use the sample command, and I'm going to sample 1 to the number of rows in the MyPIMA data set. And I want to take out roughly 80% of that. Okay, and so n row my PIMA, the number of rows in the data set, times 80%. Okay, now you could have taken out, you know, 2/3 or 66% of that, or you could have taken out half, and I'm just choosing 80. Like I said, the hold up method is it's rather arbitrary. We want to make sure we have enough left to train on. So here I'm going to create two new data sets. One is going to be called PIMA train, and that's going to be my PIMA. It's going to be all of the training indices I just picked out of my hat, so to speak. And then my test set is going to be my PIMA, whoops, everything that is not in the training. So I can use that logical not in the index formation by just putting a negative in front of there. So it will take everything that was not picked up here, okay, and it will include it. And if we want to make sure, what we can do is we can say dim PIMA train. It's always good to see if the dimensions make sense. PIMA test. And so let us see what this looks like. And that's roughly exactly what we would kind of expect. So, you know, 1/5 is here and the rest is here, and so we're okay. The other thing I want to do is translate the response to 0, 1 coding so that we can eventually calculate the misclassification rate. Okay, so now it turns out that the functions that we're going to use to do discriminant analysis can use a formula. So we can actually keep the data set PIMA train and PIMA test just like they are, and use the formula notation and pluck out the response and write the formula accordingly. But we eventually want to calculate the training and the test errors. So for that reason, we're going to have to create our own variables here for doing that, for the purpose of doing that. And I'm going to call this y.train. Okay, this will be our, let's call it y-train true, the true y for the training set. Actually, it's more natural to do it like this, I guess. Y, I like to use underscore, y true train. And for this, if I do names, PIMA test, names PIMA train, they should be the same, right? But I want class. I want to actually convert class. So if I do PIMA train class, that's our response. We see that it has these level factors. Now, let's just see how this is done. So here I have diabetic and normal, 2 factors. Now if I do as numeric, PIMA train class, okay, let's just take a look at this. The last 3 or 4 are diabetics, and so those are actually translated to ones, okay. So if we want to get a 0, 1 thing, and this is one of those things that I mentioned to you. If I do as numeric, it starts at 1. It converts the first one in alphabetical order, which was diabetes, okay, right? Diabetic. It converts that to a 1, and it converts the next one in alphabetical order to a 2, which was healthy or normal or whatever. So we need to get this on a 0, 1 scale, so we can simply do as numeric minus 1. Okay, and now we have exactly what we need. So we've converted this accordingly. And so what we want to just do is use that. And now I want to always make a note for myself here, because otherwise I'm scratching my head and thinking, okay, which one was the 0 and which one was the 1? So I usually write here, I put diabetes is 0 and normal or is it healthy? I forget. Normal is equal to 1. Okay, so that's the coding scheme. That's so that I know when I go to revisit this, or if I'm doing any downstream analysis where I look at sensitivity and whatnot. So here we can do Y, true, train, and we can do the same thing with the test, and we want to make sure that we translate them exactly the same way, and we can just change this to test. Okay, and now what we've done is we have a data set, we have a test and a training, and that includes kind of all of Y together. And now we want to, just a second here. Okay. Now we want to go ahead and fit some models. Okay. So the first thing that we will do is we will use linear discriminant analysis, which, if you remember, had the assumptions we made there was, of course, the data was Gaussian. Okay, so that's. We also used we use this common covariance matrix. Okay, and so we want to fit those boundaries, if you will. And this was relying, it used a little bit more of the data in terms of, it relied on a prior and all different types of things, means and covariance computed from the data. And this common covariance was saying that there was this kind of common covariance that was not class specific. So if we do help LDA, we see that this is actually in the function mass, which is a very rich library. So we can use this. It's a well-kept function to our advantage. We can put it in a formula. We give it the data. This is a lot of this stuff is dealing with some bells and whistles that can be added. The actual computations for LDA depend on the singular value decomposition, which we talked about when we talked about principal components, for example. They talk about that a little bit in your book. I decided to skip that this year. I've taught that in the past, but it was a little bit tangential. So here, some other things that we can do. The output, we don't actually get the decision boundaries necessarily, but we get some of the quantities that are used, including the prior, means, a scaling factor. We actually get the singular values, and the call, which is basically what you feed back into it. And there's an example here. So we're going to use this. It's a very simple function, LDA.fit, and we do LDA class twiddle dot, meaning I'm going to use everything in the data set, and the data is going to be Pima train, and I'm going to fit that model. And then once I fit the model, because if I do names, LDA fit, okay, I get all of this stuff. Actually, I think I can, let me see here. Summary LDA fit. Okay, it gives some information here. This is all the value stuff that we saw before. And yes, okay. Well, here's the prior probabilities of the class. You can actually mess with these if you want to. But we can see that there's kind of an imbalance here in the class, but it's not terrible. So here, what it doesn't give you is the fitted values, if you will. So if we want to compute the training error, we actually have to use the predict function. And I'm going to call this object LDA pred train, and I'll use predict. And if we want to figure out how to do the predict function with respect to this particular function LDA, we just use the general predict function .lda is kind of the extension, and it will tell you exactly, the syntax. Because sometimes they call it new data, sometimes they call it new X. I don't know, but here they call it new data. So we do LDA fit, and then we just feed back in the training data. And these are going to give us the training predictions. Okay, so if I do lda.pred.train, this will give us the predictions. And okay, let me just see about this for a second. Okay, so this is going to give us, this actually gives us, I believe, a log posterior probability. So I can see that there's different objects here. I was expecting to see a class label here, but I can see that there's a log posterior assigned to each value, and then we have also this class, which is what we want. So actually, let's just go back to predict.lda. And let's just take a look here. And we can see the values. Okay, these are the posterior probabilities. The class, which is the actual estimate. And scores. So let's see here. So I'm going to create another variable here, which I'm going to call let's see here, y hat train. So because we have a y true train, so let's just have a y hat train, our estimate, and that's going to be LDA pred train class, and let's just see kind of what that looks like. Y hat train. Okay, so this is looking like now something that we would expect to see. And actually, sometimes when I like to see how things are doing, I actually put it together in a matrix so I can look at y true train and y hat train. So actually I have to do it like this, as numeric. LDA pred -1 because we have to make the conversion. And now I'll go back and do that. And I can kind of see the pattern of misclassification in a binary form. Of course, this doesn't give me an overall measure on the accuracy, but it is informative. I actually look at these plots a lot. So we have our y hat train, and now we have to get our y hat test. And so in order to do that, I'm just going to copy and paste this actually, and I'm going to change this to test, and I will change this one to test for the test data, and I will make sure we're operating with the test. I typically try to avoid copying and pasting because I always forget to change something. But for this one, I think we're okay. Okay. And so let's do the same thing that we just did and cbind the y true test together with the y hat test and see how they match up. Not bad. Okay. So we can now compute the error. And if we want to do this, we can simply, I'm going to call it LDA train error. And this can be, if we think about what we just plotted here for the training error, for the test error rather, we'll do the same thing for the training, but we're looking at the absolute value of the difference between y hat true. Sorry, I really messed this up. I've got to sneak back up here and figure out what we called it. y true train. Okay, minus y hat train. So here we're looking at just the disagreements, remember? So these, if we do this, we see all of these ones. Those are all the errors, right? And so we want to actually sum that up. It's a vector. And if I look at this, it will tell me the absolute number of errors made, 95, but it's relative to the length, right, of y true train. You could have used y hat train. They're both the same length. That doesn't matter. Or you could have just wrote 423 or whatever the number is. But try to make it so that if you change something, you don't have those numbers in there that all have to be tuned again. So we have a training error of roughly 0.223. So I'm going to say 0.22. 0.22. 22% error for the training. Now we're going to do the same thing, and I'm not going to copy and paste. Test error. And so we start with the difference, the absolute difference between y true test minus y hat test. Okay, and now we have the sum of the absolute difference between these two, divided by the length of y true test. Okay? All right, so let's see what this is. Oh, it's actually lower. This is unusual, but it can happen. So, might be just an unfortunate split. Let's take a look just to make sure that this is the case. Okay, it looks like it's matching like it's supposed to. Okay, so so this is roughly 0.17. Okay, and so this I was not expecting. Of course, when I ran it this morning, it was not lower, but I probably had a different split. But this is a nice demonstration, actually, of this unfortunate split stuff and how sensitive the error can, in fact, be to the splits in the data. And in this particular example, we have an imbalance in the data set, and so that also can throw things into kind of a weird state. But it's certainly okay. And so I'm going to run this again from the beginning, except I'm going to take a new data set and let's just see what the training and test error is. Okay, and here we see that the test is above the training. So it just depends on the split, and that's okay. All right. And so I'm going to save this actually. I'm going to call it DA comp. I'll just say DA example. Okay. All right. Now, the next thing I want to do is I want to think about, okay, so this is the error for discriminant analysis. Let's go ahead and implement quadratic discriminant analysis. And so this is assuming now that the covariance matrices are kind of class specific. And in order to do this, we actually use the same package, the mass package, and we use a function called QDA. And it's the same exact syntax, the same usage. It's very simple then to write a fit, which is, sometimes I write an arrow, sometimes I write an equal sign. It doesn't really matter. It starts to matter if you start writing functions, but for now, I don't know. I just use this arrow sometimes. But, so the class, the data is the same. It's the Pima train. And if we want to predict the data set, the training set, predict, we have QDA.fit. The new data is going to be the Pima train. Because remember, for the same reasons, we can't get the predictions out. And we're going to follow kind of the same situation here. We're going to do the prediction, then we have to make y hat train. I'm going to overwrite this, okay? I mean, it doesn't matter. I know what the error is now, so I just, as opposed to having a million different variables, I'm just going to overwrite it because I don't need it anymore. But this time, what I'm going to do is I'm going to convert this, the class, -1, because, okay, let's run this first and then I'll show you why. So if I do names, QDA, pred, train, I can see that we get an output of class and also of posterior. So we want the class predictions. We want to convert them to numerics. And, here's our y hat train for what we need to calculate our training error. And then we'll do the same thing for the test set. Okay, and so QDA.pred test. We're going to use the predict function again with QDA fit, our fit that we did, and the new data in this case is going to be Pima test, and y hat test is going to be as numeric the QDA pred test -1. I forgot my $ class here. All right, so we run it again, doesn't matter. Okay, so now I just like to make sure sometimes that things are running okay. So that looks, looks okay so far. But now we want to compute the error. So we just run through the same thing. And now I'll call this QDA train error. And we can look here then at the absolute value between y hat train minus y hat test. Okay. Okay. All right. And you know what? I can actually, I know, I'm teaching you how to copy and paste, but I can actually use this because I wrote over the errors here, but I save them here in these LDA objects, so I can always bring them back up. But I can simply use the same thing. Likewise, for when I do the QDA test error, I can use this just like that because I've written over these y hats and the y trues stay the same because we divide the data into test and training first and then we go through the different methods so we're comparing on the same split of the data anyways. And so what we can do here is the same idea as we have QDA train error and QDA test error. Okay, and so let's go ahead and run this from here. Okay, and now I just want to look at this one again. Okay, so we see some differences. It looks actually, in both cases, the test error is bigger now because I went to a different seed, so it would seem more natural. So this is telling us in this case that it's pretty close. It looks like in this case QTA does a little bit better, but I'm sure that's not significant. So LDA does fine. Um, and so, let's just run it one more time. So what I'm going to do is I'm going to run all the way up to before the seed, to after the seed, because I don't want to reset the seed, otherwise I get the same result. So I go here and I take another split of the data. Okay. Okay, and now I can see that the test error is lower again and the training is higher. But let's see, in terms of performance, it looks like QDA again does just a little bit better. And so maybe what I want to do here is change this to something a little bit different. Let's see if I can get some more stable results. Okay, so now what we're doing is we're just resampling test and training over and over. And it looks like it's at least stabilizing a little bit. It's staying in the low 20s for every split. So from doing that, I might decide that, 2/3 might be a better split. Okay. But in terms of performance, it's kind of looking like they're almost the same. Not too much difference. Okay, but we did both. Okay, and now for this case, there's only 2 classes, right? So, it's not like we had to do a ton to get, all the different covariance matrices. There's only 2 in this case. The last thing I want to show you is just kind of for completion. Even though the package is not running correctly, we can start to fit the functions. And so what I'm going to do is I'm going to introduce this to you. I'm sorry, I'm showing you my cheat sheet, but I need to get down to the bottom so I can see the commands, and I can see why I can't do that. Okay, I'm going to show you how to do the regularized discriminant analysis. And what I hope is that the author will get back to me. You never know if they do. It's kind of like a volunteer thing to do it. But I want to introduce the function and talk about it for a minute, because I really like this method. When I do a help RDA, which is the function that we're going to use, this will come up. And now you have to be a little bit careful. If you do a Google search for RDA, or regularized discriminant analysis in R, you're going to end up with a package that doesn't do a very good job. It's by the people who wrote the book, and it's kind of built for high-dimensional microarray data, and it has very poor support in the function, and I really don't like the package. So I'm really sticking to this one, even though we can't do the prediction with it. I want to talk about it, and I hope that we can eventually get it running. But I just want to point it out. The formula, there's a bunch of stuff here. There's this simulated annealing piece in the search, if you want to search for an optimal value between the two. But what we're going to use it for, we can input the formula, we can change the priors and whatnot like we did before. We're going to actually fix the values, and we're not going to do an optimization to find them. We're going to fix the values, but this is what I wanted to show you. The 4 extremes, this is exactly what we talked about. We can actually monitor these. Here they write it a little bit differently than we wrote it, but we see this compromise between the pooled covariance matrix and the individual covariance matrices. And so lambda is actually dealing with that compromise. So these two will give us the QDA and LDA solution, and then there's anything in between will give us an RDA. So what we're going to do then, and gamma in our case is always going to be 0, incidentally. Okay, so I will show you. We're just going to do an LDA fit using RDA. So this is kind of like a really cool function because you really only need to learn this and then do the special cases of it. And in fact, I used to teach it like that until it broke, and it's been broken for a little while. So the term is called regularization, just as I usually call it. Gamma is equal to 0 and lambda is equal to 1. This is the LDA fit. And for the QDA fit, we're just going to change this to 0. And if we wanted to do an RDA fit, say we wanted to have something that's exactly in the middle, a compromise between the two, we could change this to 0.5. And now we have done all three fits, just like that. And LDA fit, okay, if I do names, LDA fit, I get all kinds of stuff, including an error rate, so we don't have to do any funny calculation there. $ error rate, okay, and then we have QDA and RDA. Okay, and it gives us these error rates. I'm not sure what APER is standing for in this case. Approximated error rate. It's just slightly different than the results before, but what we see is the same idea. This is the training error rate. And if you do a help RDA, you might say, well, it doesn't look like it's broken. It actually outputs the error rate, which is nice because we don't have to compute it. But what happens is the predict function does not work. So if I do predict LDA fit and I give it new data, Pima test, oh my gosh, it works. Okay, this was surprising. Hang on a second. I feel like there's something wrong. Okay. I'm going to call this mypred. Okay. Names mypred. Okay. All right. Let us see if we can look at mypred. Class. Very interesting. Okay, so it appears that it is working. I'm not exactly sure why it wasn't working before. So this is good. So this is mypred for LDA. And we can do the same thing for mypred QDA and RDA by just changing this. QDA and RDA. Okay. And let's just take a look. Okay, it seems to really run without complaint. One problem was I might have had a test or training set that was too small because I was using 80% before, and I'm not sure if that kind of put things into a problem region. So anyways, hopefully this also works on your computer. We have this going now. We have predictions, and so we could find the test error. Okay, so I'll just call LDA test error, QDA test error, and RDA test error, and we can compute that. So let's first do y hat LDA, and let's do it like this. LDA y hat test, and that's going to be mypred LDA class as numeric minus 1. And we could do the same thing to get the predictions for the other three. So I'll change this to an RDA and a QDA. This is a QDA and an RDA. Okay, so let's see. And to compute the test error, we can look at the absolute value of this. And I have to look at the difference between that and the true test error, which I have to remember the notation. Y true test. Okay, so we'll grab that. Minus. So we take the absolute value and the sum, and then we can divide through by the length of this one. And now we can actually do the same thing for the QDA one. I'll change this to the QDA, and the same for the RDA. And then finally, let's just take a look at this comparison. Because it was just a tiny bit different, I'll put the test error. And so I'm just going to run it from here. Now the training error rate is right here. We don't need to do anything there. Okay, and we can see that it's almost exactly the same, which is not too surprising actually, because the training error was so close. So it seems like the fits are almost exactly the same in this case. So, and you know, we can get test errors that are almost the same or the same, especially when we have a smaller data set. And you have to think that this is also the misclassification rate. So they might not be getting the same exact ones right and wrong, but overall the sum is the same. So we see that they are equivalent in this case. And so that is basically all I wanted to talk about with respect to these three different methods. In the next lab, I will go through logistic regression. Thanks.